Hello everyone, my name is Dmitry Podborsky and this is the presentation of our ACM Multimedia Systems Conference demo track paper with the title Cloud Rendering Based Volumetric Video Streaming System for Mixed Reality Services. In this talk I would like to speak about a cloud rendering system for volumetric content. So let's talk about volumetric content first, since there are different representations how volumetric video can be constructed. So we are using a mesh-based volumetric video. So our video consists of a sequence of meshes with the corresponding sequence of textures, which when rendered together result in a volumetric video which you can then use in your scene and have full control of. In order to prepare the content, we take those textures and encode them as a video using, for example, H.264 video encoder. And we do the same for the sequence of meshes, where we use a mesh encoder to compress the data. So we have then two elementary streams, which we then multiplex together into the single MP4 file, which then has two tracks, for example, one for video textures and one for meshes. Of course, there might be a third track representing the audio of that sequence as well. And on the client's end device, when you would like to render your volumetric video, you have to do those steps in reverse order. And the biggest problem currently is that so far there is actually no hardware decoders available which can deal with volumetric video. And of course there's some effort in MPEG utilizing the video decoders available on your client's end device. I'm speaking here about video-based point cloud compression work, which is really good. However, this still has some problems because you have to run several decoder instances in parallel, which also might be a bit tricky. So it might have some synchronization issues, it might have some issues when one of the decoders drops a frame. And also, if you deal with multiple volumetric objects on this client device, then it's gonna be really complicated if you use, for example, just 3 decoder instances for a single video. So this doesn't scale very much. So there's simply not enough processing power on mobile devices nowadays to deal with the really complex scenes with many objects and so on. And even though the work done is pretty impressive, the bit rates of compressed volumetric video objects is still too high. So those problems needs to be solved somehow. And one of the solutions which we actually would like to emphasize in this talk is based on the cloud, right? So when we speak about the cloud, we actually have like unlimited power. So we can actually shift all the processing into the cloud server and it can be really powerful. So we do all the volumetric video processing, the multiplexing, decoding, rendering, so everything done can be done on the cloud. And the client would then send some control data to the cloud, for example, tell that it changes the viewport or it interacted with some objects. And after the scene is finally rendered, taking into account that received control data, 2D video stream is sent back to the client. So the client at the end just needs to decode a simple 2D video and still has control over the scene while sending this control data and controlling the rendering process on the cloud side. Okay, enough talking. Let's go more into the detail of the implementation. And I would like to show you this figure here, which shows how all of this is implemented in our system. And in this figure, you can see here we have a server part. On the left side, we have a client part. Let's talk about the server first. It's in our current implementation, we actually have a cloud rendering library, which is actually a SDK, which runs on Linux, Windows, and macOS. And we are using this cloud rendering library. We have implemented a native plugin for Unity, which you can embed into your Unity application. And in our Unity application, we have implementation of this volumetric video player, which takes the MP4 file with the different tracks, video track and mesh track. Then it demultiplex video and mesh. Then it decodes those two and renders it to the scene, and the camera which is rendering the scene is then rendering to the render texture, and that render texture is then pushed into the library. And inside the library we're using the GStreamer framework, which is a really powerful multimedia processing framework. And below here you can see the media pipeline. The render texture goes into the app source, which is the source element for the media pipeline in GStreamer. We convert the texture for a YUV format to prepare it for encoding, and then it's encoded, moved to WebRTC block, which is basically creating the RTP stream and send it back to the client. And for the data stream, we are using WebSocket. So we have in the library, we have a WebSocket server, which accepting incoming client connections. And we have like object registration. So the application in Unity can say, for example, with what kind of objects the scene has and allows to control. Those are registered in some pool and controlled. And the client basically has a control of those objects. And then we have some prediction engine which does the prediction of the viewport, etc. And on the client side, we have implemented two different clients. We have a web browser-based implementation, which is a simple JavaScript, like a web browser page. And then we also have a HoloLens implementation. And the architecture itself looks similar, so we need, of course, the WebRTC part, which receives this bit stream, video stream, decodes it and renders. And we have a WebSocket connection, which deals with all this data stream, data traffic, signaling data, user interaction data, and so on. Of course, everything comes with a price. And in our case, the highest price we have to pay is the motion to photon latency. And this is the time between when the client first requested the server to change the scene until this change is really visible on the client's end device. And this has to be as low as possible, because high values of motion to photon latency are crucial and will destroy your quality of experience completely. So our good friends, in order to cope with this problem, are of course hardware video encoding. So we use NVIDIA encoding API to encode video on the hardware. We use WebRTC for ultra-low latency streaming. We also do experiments with 5G as well, since it also has some nice features regarding low latency. And we also have to do some viewport prediction. So we have to predict the future position of the user even before it happened. And on the client side, post-rendering correction methods can be used in order to make video look better. And just to emphasize, how do we measure the motion to photon latency? For that, we created a web client application and a console application for the server. And the idea is as follows. So the client establishes the data stream connection to the server. After this, the peer-to-peer connection is established and the server starts streaming the video. In this case, we're gonna just stream the simple bars. And then the measurement process actually starts. So the client requests the texture color to change. And as soon as this data goes out of the client, it starts the timer. So this data goes to the server, changes the color, goes back, and as soon as the green texture is detected on the client side, we stop the counter and measure our motion to photon latency. And I'm gonna show the implementation of this just in a second. Okay, let's move to the demonstration itself. So as you can see here, the project we are working on is kind of huge already. So we have inside the project the cloud rendering library implementation with all the modules. Then we have for embedding to the Unity, we have a Unity plugin. We have a console application which we use for motion to photon latency measurements, as I explained in the previous slide. And obviously we have Unity application itself embedding this cloud rendering library. as a DLL, and we have also several web clients. I'm gonna speak about this 2D web client today. So all of the web clients are using a split rendering module, which is our JavaScript module which you can embed to your website. And let me connect to the server and show it how it looks like. So we're gonna use a telecom server, which is also connected to 5G network. Okay, so on this machine here, we have, as you can see here, NVIDIA encoders plugins for GStreamer enabled. And our application, the Unity application, is compiled in the as a Unity project. Looks like this. So if you execute it, it starts with the main scene, basically where you can configure your application before you start the streaming session. So you can select several scenes. In the case we are interested right now in the volumetric player. So you can select your source file. In this case, we have a Josh sequence and set some parameters and then click start. So you can see the video here, so you can actually also on the server side navigate through the scene yourself, but we are more interested in how to use this from the client side on your client PC, right? So I'm not using 5G here, I'm just connected to a Wi-Fi. Let's go to the Chrome browser, for example here, connect to we go to the HTTP website located on this telecom server as well. As you can see here, this is the 2D client implementation, how this website looks like. And here you can select the server which you would like to connect to, and then you just click connect. Now the connection is established and you can see the volumetric video, so you can navigate through it, so you can rotate the volumetric object, you can drag and drop. So this is a kind of 3GS simplified view of the scene, and using WASD controls you can actually fly around and see the object from any perspective you like. So as you can see here, it's quite responsive, so I kind of can move right, left, forth, back, up, down, then I can rotate the object and so on. So this is actually how it works. Okay, a 2D video client is a really nice thing to have, but what we're actually really targeting at the end is an augmented reality application. So we have started to experiment with the HoloLens, and in this short video here you can see the first prototype working. So it will render the 2D video on this plane, which is put into the AR environment, so you can freely grab and drag and drop this plane in your viewing space, and then we remove the background, so the object seems to be not rendered on the plane in this case. And then if you walk around, you see it from different angles. So the camera view on the server side is doing exactly the same as it did and for the 2D video client as well. So the quality, as you can see here, is not the best, but we are improving it. So it's the first prototype implementation which you see here. And we also have started to work on WebXR clients, which are doing the similar things but in the web browser. The next thing I would really like to discuss with you is how to measure the motion to photon latency, because this is one of the most important metrics for such a system. Okay, so for the motion to photon latency measurements, I would use Amazon Elastic Cloud instance. Let me quickly connect to it. Here we can execute our console application. And now we go to HHI-demo.de, which is a domain also pointing to the same web server located on the same instance. Connect, go to the latency measurement page, select HHI-demo.de, running on port 8080, connect to it. So now we see we connected, and we receive this black bars. And now, as I explained in the previous slides, the client will send control data to the server to change the color and wait until this finally rendered on the screen, and then stop the counter. And it will take 50 independent measurements. So let's try it out. So as you can see here in this example, we run 50 independent measurements, and we have a motion to photon latency measured on average about 68.45 milliseconds. Okay, that's it. Thank you very much for your patience, and please stay healthy. Bye bye.